What do the words glucogenesis and glycolysis actually mean? I've mentioned both of these words in a few of my past videos when referring to fructose and galactose metabolic pathways, but now is the time for me to actually go through both the glycolysis and glucogenesis pathways separately as their own one big video, because it is a massive sort of process and there is quite a bit to cover and it may take a while. Who knows? I don't really know how quickly I'm going to go through this, but whatever. But the meanings of glycolysis and glucogenesis are quite interesting. Glycolysis, if you sort of split it up, the sort of glyco part just means glucose, but the lysolysis means breakdown. So glycolysis essentially means the breakdown of glucose, and glucogenesis, you've got the sort of glyco part, which just means glucose, and genesis means production, so the production of glucose. And I'm going to go through both of these inside of today's video. Now I'm going to start with glycolysis and the sort of glycolysis pathway, because that will make things a lot easier to understand come the sort of endpoint slash middle of this video. But of course, when it comes to glycolysis, obviously you're starting with glucose, and glucose can come from a variety of sources. It can come from fructose, it can come from galactose, but all of this I'm going to sort of go through towards the end of this video. It's this sort of glycolysis and glucogenesis is a very interesting topic, and I'm going to dedicate as long as I possibly can to going through this as thoroughly as possible. Now, the first step of the glycolysis pathway, the breakdown of glucose, is glucose turning into glucose 6-phosphate using the enzyme hexokinase. Now, as I said before, kinase essentially means you're just adding a phosphate group onto the molecule, but hex means 6 in a lot of the sort of numerical and dimensional cases, and that means that it ends up being glucose 6-phosphate rather than sort of glucose 2-phosphate or 3-phosphate or whatever. But you also have an adenosine triphosphate molecule on the left side of the reaction, and this ends up producing an adenosine diphosphate molecule, and that's essentially where glucose 6-phosphate gets its phosphate group from. Now, the second step inside of the glycolysis pathway is glucose 6-phosphate, which can be abbreviated to G6P, ends up turning into fructose 6-phosphate using the enzyme phosphokinase isomerase. Now, I may have mentioned fructose 6-phosphate in a past video on the fructose metabolism, and this is where fructose becomes very important for the production of glucose, because fructose 6-phosphate can enter the glucogenesis pathway to end up sort of doing the reverse of these reactions to end up producing glucose. But that will make a bit more sense come the end of this video. But now you sort of see how all these different metabolic reactions just end up contributing to each other in a variety of different ways, which is what, to me personally, makes science incredibly interesting when you consider the biology and anatomy of our body and our different chemical reactions and so much other different stuff. Now, the third step inside of the glycolysis pathway is fructose 6-phosphate ends up turning into fructose 1,6-biphosphate using the enzyme phosphofructokinase. And just like the first reaction step, you have an adenosine triphosphate molecule end up turning into an adenosine diphosphate molecule, because obviously now it's a biphosphate, it has an extra phosphate group, and this means that it needs the sort of ATP-ADP thing to end up getting that phosphate group to become a biphosphate. Now, the next reaction step, the fourth reaction step of this sort of glycolysis process, is a very complicated one, and you start with fructose 1,6-biphosphate, and this ends up turning into G3P as well as DHAP. Now, it's completely escaped me what G3P and DHAP stand for, but I had to abbreviate this sort of stuff in my script book, because otherwise it was going to end up taking far too much space and be really way too inefficient. But this reaction is catalyzed by the enzyme aldolase, and what's also interesting is that G3P and DHAP, while they are two separate molecules, they can sort of turn into each other, and this is a sort of reversible reaction catalyzed by the enzyme isomerase, and they just sort of turn into each other. And yeah, that's a very interesting thing. I'm not really sure how that exactly contributes to the glycolysis pathway, but it's just another interesting fact about the stuff that actually happens inside of the cells in your body. Now, the fifth step inside of the glycolysis reaction process is G3P turning into 1,3-biphosphoglycerate, and this reaction is catalyzed by another very complicated enzyme with an incredibly long name but I'm going to abbreviate the first part, so it is just G1,3P dehydrogenase. And similar to the sort of ATP, ADP thing that we talked about in a few earlier reactions, this has a similar sort of process, but it's just using a slightly different molecule known as NAD, and NAD is essentially the equivalent of adenosine triphosphate, and that turns into NADH. Now, adenosine triphosphate and NAD, NADH, NADPH, and NADP, these are essentially the mitochondria, which are things inside of your cells. These are the things that they can use to either produce or use energy, calories, etc. It's all a very complicated process. I'm going to go through how NADH, NADPH, etc. work completely in their sort of advanced states in a whole separate video, because it does deserve a whole other video of its own. But for now, you just need to know that when adenosine triphosphate turns into an adenosine diphosphate, it ends up using energy. But when adenosine diphosphate ends up turning into an adenosine triphosphate, you end up gaining energy, and that reaction ends up being used as sort of energy for your body to be able to move on a daily basis, which I find fascinating and very, very interesting. But as well as the sort of energy being used or produced can apply to ATP and ADP, it can also apply to NAD, NADH, NADPH, and NADP. Now, NAD, in the reaction we just spoke about, ends up being turned into NADH, and that means that it has had a hydrogen molecule being put onto the sort of NAD molecule, because NAD is actually a charged molecule. I was probably supposed to say NAD+, and that means the plus ends up being gone when you add the hydrogen molecule to turn it into NADH, and you sort of need the hydrogen molecule to be added because that's just something that's necessary for that sort of metabolic reaction to actually be useful. But NAD and NADH, this reaction ends up producing energy. NAD going to NADH ends up producing energy because NADH is essentially a better molecule for your body to have compared to NAD. And it's the same sort of thing as ATP and ADP, just with NAD and NADH, which is something that's very, very interesting. And as I say, I'm going to go through that whole sort of process of different sort of NAD, NADH, the sort of mitochondria stock market or whatever, in a whole separate video, because that is something that it definitely deserves. Now, the sixth reaction step inside of the glycolysis pathway is the 1,3-biphosphoglycerate ends up turning into 3-phosphoglycerate, and this is where things get interesting, and you sort of start to see how that sort of ADP, ATP, NAD, NADH thing actually starts to work, because on the left side of the reaction, you need an ADP molecule as well as an inorganic phosphate group, and this produces an ATP molecule, and that means that this reaction actually produces energy rather than consumes it. And this reaction is also catalyzed by the enzyme phosphoglycerate kinase. And this is where, from this point onwards, as well as the last reaction step, step 5, these reactions end up being used to produce energy. Not all of them, I'll say specifically which ones, but I'll explain it once I end up completing the glycolysis pathway. Just stick around for another 3 to 4 minutes or so to sort of get that exact explanation. Now, the seventh step inside of this glycolysis pathway is the 3-phosphoglycerate ends up turning into 2-phosphoglycerate using the enzyme phosphoglycerate mutase. Now, this doesn't really add nor take away a phosphate group, but what I personally find quite interesting is that it simply switches where the phosphate group is on the molecule. You may notice that the number from 3 to 2 actually ended up changing, and that's because the mutase part of the phosphoglycerate mutase enzyme simply just switched where that phosphate group was on the molecule. I just find the fact that that happens in our bodies just incredibly interesting. I don't know why I'm so obsessed with science in this weird kind of way, but it's just how I seem to be as a person, and yeah. Now, the eighth step inside of this glycolysis reaction, metabolic pathway, whatever you want to call it, is the 2-phosphoglycerate ends up turning into phosphophonyl pyruvate, and this uses the enzyme aldolase plus a magnesium ion. Now, we haven't really talked about ions in any of the sort of reaction processes that I have mentioned in previous metabolic pathways, but you need a magnesium ion to actually contribute to this reaction happening, which is interesting because this is one of the reasons that nutrients, etc., are so important in your diet, simply because if you didn't have enough magnesium in your diet, this reaction would not exist. this reaction would not be able to happen, and you wouldn't be able to get the maximum amount of energy that your body could possibly produce by this sort of the next reaction after this one being able to happen, simply because you had phosphophonal pyruvate, because you had the a sufficient amount of magnesium ions. That's another thing that's incredibly interesting about diet, nutrition, science, etc. And yeah, it just seems to blow my mind, and I hope you kind of can resonate and relate to me with that sort of thing. And the ninth and final reaction step inside of the glycolysis pathway is phosphophonal pyruvate ends up turning into straight up pyruvate, and this uses the enzyme pyruvate kinase. Now, this reaction, you have an ADP molecule on the left side and an ATP on the right side, and this means that this reaction ends up producing energy. When you sort of have the ATP, NADHs, those reactions are normally the ones that either produce or consume certain amounts, or at least larger amounts than normal, energy. And you may have noticed that there were only 2 reactions where it was ATP getting turned into ADP, and there were 3 reactions where it was NAD turning to NADH, plus 2 more reactions where it was ADP turning into ATP. So that is 3 versus 2. There were 2 reactions that ended up consuming energy, and 3 reactions that ended up producing energy. So what exactly does glycolysis do to your body? Glycolysis produces energy, and this happens in pretty much every single cell inside of the cytoplasm of your body, and that is used to power your muscles, get you through your gym workouts, just get you through the general day. And yeah, that's just an incredibly interesting thing, which I find fascinating. But what's interesting is that for one glucose molecule that goes through this metabolic process, 2 pyruvate molecules end up coming out at the end. So you essentially just 2 times the sort of net energy yield from this metabolic pathway. For every 1 glucose molecule, 2 pyruvate molecules are produced, and 2 ATP molecules are produced as a sort of net yield, as well as 2 NADH molecules. And this is mostly because one of the steps, I think it was step 4 or step 5, the step where G3P and DHAP were both produced in a single reaction, DHAP can essentially turn into G3P. And this means that every single time that both G3P and DHAP are produced, the DHAP will turn into G3P. And this means that you basically get the 2 pathways. So the one pathway that happened previously that we kind of talked about going through this video, you essentially just 2 times that process, because every single DHAP molecule that is produced in that step 4 or step 5 reaction just will turn into G3P eventually, and so you end up getting a 2 times energy yield. It's quite interesting, but it's quite complicated, and so I hope I have explained it as best as I can. But we haven't even got on to glucogenesis yet, and we're already probably around 15 minutes into the video. But the thing is that glucogenesis is not all that different from glycolysis. There are only 5 changes to the sort of thing that happens, you know, the 9 steps that we talked about earlier. There are only 5 enzymatic changes and a few other little things that mean that glucogenesis is slightly different to glycolysis. Because as I said a little bit earlier about the fructose 6-phosphate, glucogenesis is essentially just the reverse of glycolysis. It's not all that different, and while there are a few changes which I will explain, it's not like completely different and doesn't really deserve its own video, because it would just sort of be me explaining the reverse of glycolysis, which would end up being a bit draining and droning if you'd already sort of watched the glycolysis video. Now, the 5 different enzyme changes happen on steps 9, 3, 2, as well as 1, and there is also just an extra little reaction which happens in between, like one of the sort of step 9, step 8, etc., which I'm going to also go through. And you're obviously starting with pyruvate, which is a smaller molecule, and the sort of going from the reverse from step 9 up to step 8 ends up taking 2 reactions, and the first of these reactions is pyruvate turning into oxaloacetate, and the second of these reactions is oxaloacetate turning back into phosphophonal pyruvate using the enzyme phosphophonal pyruvate carboxylase. Now, oxaloacetate is a very interesting molecule because oxaloacetate is produced during the Krebs and citric acid cycle, and I will put an image up on screen, but when acetyl-CoA ends up going through the sort of citric acid cycle, you get oxaloacetate, but instead of going to citrate, if you were on a ketosis diet, a carnivore diet, oxaloacetate is going to be used to sort of produce the phosphophonal pyruvate, and it's going to go through glucogenesis to end up producing glucose, because obviously you're not actually eating any glucose from your diet if you are on like a carnivore diet, no carb diet, ketosis diet, or whatever. You simply won't have enough glucose, and so oxaloacetate is going to end up producing phosphophonopyruvate instead of citrate, which ends up going through the rest of the sort of glucogenesis pathway to produce glucose, which is able to fulfill your baseline blood glucose levels. But the sort of enzymatic reaction changes are the reactions step 3, 2, and 1, and this is fructose 1,6 biphosphate turning into fructose 6-phosphate, fructose 6-phosphate turning into glucose 6-phosphate, and glucose 6-phosphate turning into glucose. Those 3 reactions have an enzymatic change. I might put the sort of enzymes that sort of catalyze those reactions on the screen, but that is essentially it. I've been recording for like 20 minutes, my throat is really, really sore right now, and yeah, that is the whole entire glycolysis pathway plus glucogenesis, and a little bit of an explanation on what actually happens during ketosis, which is like a nice little fact that you might want to know if you're going to sort of try out those kind of diets instead of sort of blindly following what other people say and actually following some scientific advice to sort of see what happens. Because you may know that when you start ketosis, you get very, very tired, and that's simply because, obviously, as I said before, glycolysis ends up breaking down glucose and producing energy. If glycolysis ends up producing energy, glucogenesis ends up having a net sort of energy consumption, and this means that when you get onto ketosis, you start to feel very, very tired, and then eventually you sort of see the benefits of those diets later down the line. And yeah, I hope you enjoyed the video, and I very much appreciate it if you have stayed about to the end. I also recommend subscribing, because I love this community of young tribal people who are willing to improve themselves so much more than they already have, and good luck.